Okay, today we'll derive the bending equation or the flexure equation. So which is given by m by I is equal to sigma b by y or sigma y by I, sigma by y is equal to e by r. I said how you can remember this equation. May I sing for you, India Raja? So you can actually remember like this. So we'll try to derive the first part of the equation here. Sigma by y is equal to e by r. Okay, we'll try to derive this part of the equation first. To derive this. Okay, I'm trying to save space so that I'll be able to derive the complete equation. So now to derive this equation, first what I do is I consider a beam. So it is a beam which is initially straight. Now this beam is initially straight. So when it is straight, will it have any stresses, guys? No load on it. It's simply lying on the floor. Will it have any stresses or not? Guys, it's simply lying on the floor without any load on it. Will it have any stresses inside? No force on it, no stresses. So initially that means that there are no stresses in this material. Okay. And now this is actually applied with a bending moment and it becomes like this. So the same thing here. So I'll try to show it like this. So this, when applied with a bending moment like this, it actually starts to change the shape like this. I'm not able to. I think it must be good. Okay. Initially the beam was straight, and now it is actually bent into the shape by applying a constant bending moment, which is called as a pure bending. Okay, I'll explain you what is pure bending. Pure bending is where the bending moment is constant throughout. So you've drawn SFD BMD. You have seen BMD is varying at some point. So at any instant you can say that at that point that bending moment is that. So that bending moment is M. That bending moment is M. Okay. Now here also you will have. Okay, yesterday we explained you. This axis is called as what? It's called as what? Neutral axis. So I'll write it as NA here. It's called as neutral axis. And now to actually derive this, what I do is I take an element here. Okay, I take an element in this beam, a small element in this beam, and that element I will name this as P, small q, R, and S. And here, this is the neutral axis. This is the neutral axis. So here, I will actually say this again. Okay, suppose if I try to redraw this small element here, that element will look like this. That element will look like this. Okay. So can I write this as P and Q? No, because the distance between P and Q has reduced. So I have to write it as like P dash Q dash. Now this distance between R and S has reduced, increased, so I write it as R dash S dash. Okay. And this distance between, the distance of the neutral axis, has it changed? Has it changed or not? It has not changed. Neutral axis neither expands nor compresses. It will have the same length here. So I write it as, okay, I will not write it as N dash A dash because it is the same length. I can write it as it is. Okay. Now, let me consider a fiber. Fiber basically is a line of metal in this big beam. Basically, this beam is like this. It looks like this. Basically, it is not a rectangle. It is actually like this. These are actually like this. Okay. These are actually like this. Okay. I'm considering a metal in this plane, which you can call it as a fiber. I'll name this as E and F. I'll name this as EF. Okay, this is at a distance y. This is at a distance y from the neutral axis. And this fiber, will it expand or contract? after bending. That will expand. So its length is not the same. So I'll write it as E dash F dash. E dash F dash. And it ensures that it also will be at the same distance y. It will not take a shortcut. It will not take a shortcut because of this expansion. It will not actually come near. So it is one of the assumptions in this. So that means this now suppose if it was a square shape here, and all the square shapes in the material will remain square even after bending. They will not become rectangle at the center. So that means this fiber, when you bend, it will not take a shortcut and go like this. It will take the same path at the same distance, so it maintains the same distance. Okay. So these are some of the assumptions. And now, before we go ahead, we'll try to say what are the equations that you use. Guys, do you know this equation? E is equal to what? E is equal to Young's modulus is equal to what? Stress by strain. So from Hooke's law we say that stress is directly proportional to strain, and the slope of that line is actually Young's modulus. Okay, that we know. And again, do you know what is the formula for strain? dl by L, change in length by L. And also if suppose if I draw an arc here, suppose if I draw an arc here, and if this theta, suppose if this theta is in radians, then can you tell me what is this length L? Length L in terms of, length L in terms of this radius R. So can you tell me what is that? What is this length? When this R is given and when this angle is given in theta radians, what is this? R theta. So this is R into theta. Okay, where theta is in radians. If you know this, then now this derivation becomes easier. So it is R into theta. If you know this, then we can proceed. Okay, now let us to find out strain. We'll try to find out the strain in this element. So to find the strain in the element, let us find the initial length of EF. Initial length of this EF, let me call it as Li. Okay. Initial length of EF is equal to this. Guys, EF, is it equal to NA? Is it equal to NA or not? Yes. Is this NA the same as NA here? Yes. Okay. Now, what I will do is, I will try to extend this. Okay, I'll try to extend this here. And when I extend this, this forms an angle d theta. This forms an angle d theta. Okay. Now, this length L, you got it in terms of radius R into theta. Now, can you tell what is this length along NA in terms of this? Suppose if I call this as the radius of curvature R. Suppose if I call this as radius of curvature R, then can you tell me what is this length from this to this point? Similar to this, what is this length from N to A? Huh? Video is recording, man. I think I'll show you who are these people later. Okay, this is length, R is length, basically. Instead of L, it is R is length. What is the angle? Theta. That will give you this NA. Okay, so I can say that initial length of EF is equal to NA. So therefore, you can write that is actually equal to R into d theta, where this d theta is in radians. Then final length of EF, so I'll call it as LF. Okay, is it the initial length or the final length? It is the initial length. Final length is this. Now up to here it was R. From here to here, what is this? Y. Now can you tell me what is the length along this E to like E dash F dash along this, what is the length? So can you tell me in the same lines? R plus y into d theta. So you can write it as E dash F dash is equal to, so R plus y into d theta. Okay. Now we have made use of this. Then we will make use of this. We know strain is nothing but change in length to the original length of the fiber. So strain in the fiber EF is equal to change in length divided by original length. Okay. So change in length is basically what? Li minus Lf or Lf minus Li. Final length minus initial length divided by initial length. So it is always the difference in length with respect to the original length. Original length is Li. Okay. So if I substitute this, is it visible in the video? Is this visible? Up to here? Okay. So Lf is R plus y d theta, and this Li is nothing but R d theta divided by Li. What is Li? That is R d theta. So what I can write here is, so R d theta plus y d theta minus R d theta divided by R d theta. So what cancels out here? This. So what is left here? Y d theta divided by R d theta, where again this d theta cancels out. So what you are left with is strain in the fiber EF, or simply strain. Let us call it a strain. Okay, in that fiber. Okay. So strain is y by, so strain is y by R. So strain is y by R. Let me call this equation as 1. Let me call this equation as 1. And then, so we have used this. So we know Young's modulus is equal to stress by strain. Young's modulus is equal to stress by strain. So what is strain now? Now as per this equation, suppose if I rewrite this equation, strain is equal to what? If I bring this strain here, then I can send this Young's modulus here. Now what does it become? It is sigma divided by E. Since strain is equal to sigma divided by E, I can replace this part here. So this becomes like sigma by E is equal to y by R. Guys, are we near to this? Somewhere? Is this equation near to this? If it is almost this, but it has changed the locations. So this y should have come here. So just change the locations of this. So you are writing this as sigma divided by y is equal to E by R. Okay. So you have arrived at the first part of the equation. So you are trying to compare these two equations. You are basically trying to compare this 1 and 2 equations to get this equation 3. So you can write. So from 1 and 2 you got this. From 1 and 2. This you got from 1 and 2. From 1 and 2 you got this. And finally this now this equation you got. So which you can call it as equation 1. So you have actually derived this part of the equation. This part of the equation you have derived. Okay. So suppose if this derivation has got 10 marks, if you derive up to this point, you will have 5 marks. So what and all assumptions we have made? So that means as you bend, these fibers will not actually slip and come near. It will remain same. That means this area will remain the same, and as well as this material follows Hooke's law. So Young's modulus is equal to stress by strain. So that means stress is directly proportional to strain within the elastic limit. So that means this material follows Hooke's law. These are the two assumptions that we already made and used here. And initially we said that this material, now this beam before bending, it was straight and it had no stresses, and only after bending the stresses have been induced. That stress is given by this equation. Okay, so the first part of the equation is derived. So let us now derive the second part of the equation. So since there is no place here, okay. Okay, okay, there is this because I am not able to accommodate, or should I do it in next place? No, I'll try to do it here only. Okay, here I'll try to move. So let me also show you. These are my students who joined engineering in 2023. Okay. No, it's good. Maybe after 10 years you can show it to your children and wife. Okay, is it visible? Okay, is it actually coming out of the view? So in some akade move madbeka. Ide urga res madbeku, ide urga. Okay. Okay. Now we'll try to derive the second part of the equation. So that is m by I so second part of the equation is trying to derive m by I is equal to E by R. So to derive m by I is equal to E by R. Okay. Now let me zoom this. Now for the first part of the derivation, we saw this front face of the beam. For the second part of the derivation, we will see the side face of the beam here. The side face of the beam. Please, I am trying to zoom this out. Okay, I am trying to zoom this. So basically, this rectangle, or the rectangle, looks like this. Okay, I am drawing this. And here I got the neutral axis. So all the fibers starting from this point are called as neutral fibers, like this. So this is neutral axis. I considered an element here. Earlier, I considered an element below here. So in that element, I'll consider an element which has got an area dA. Now this element has got an area dA, any sort of shape, and this element is at a distance of y from the neutral axis. Okay. Now you know that since this material is bent like this, here you will have the tensile forces. Here you will have the compressive forces. Okay. Now, if this element, suppose if this area is here, suppose if the same area I am showing here you will have a force which is actually tensile, which I call it as the normal force Fn. Okay. That is the force at this, which is actually at a distance of y from this neutral axis. And here, I will try to use the equation sigma is equal to what? So what is the formula for sigma? So force by area or load by area. You call it as P by A or F by A. So if I know Fn, if I know for this elemental area that there is a normal force which is coming out, which is Fn, then I can actually denote this Fn using this equation as sigma into A. Sigma into area. But I've already from 3, that means from this equation 3. From equation 3, I already know that sigma is equal to what? Sigma is equal to what? So E by R into Y. So let me substitute this sigma value here. So this equation becomes Fn is equal to E by R into Y into basically this is elemental area dA. So I'll write this as dA here. So this is dA. Okay. Now Fn is equal to sigma into dA. So substitute this. Now, you know what is moment? Moment is what? Basically, moment is actually force into this distance. Force into distance will create a moment. So that is the, if you add all these elemental areas multiplied by the forces which creates moment, if you integrate all that, that will become the total moment here. So, the differential moment created by this Fn force on this elemental area dA can be called as dm, which is actually equal to Fn into y, where Fn is the normal force from this element and y is the distance, because you know moment is actually force into distance. So I will substitute this here. So if I substitute this here, this becomes like E by R into y square dA. It becomes y square dA. So I got this elemental moment due to this small element. If I want it for this whole area, then I should integrate this with respect to this y, where y is the distance between, from this neutral axis to this, so that is from 0 to y. Okay, so if I integrate this dm, then I get moment. So I have to integrate this part. If I integrate this part here, Young's modulus is a material property. So what is the Young's modulus of steel? It is 200 GPa. So it is a constant. You don't integrate constants. And what is R? Radius of curvature. That is again a constant. So you don't integrate it. So that you have to take it out of integration sign, E by R, and you have to integrate this y square dA. Now I should have told you initially that this integration of y square dA is nothing but the moment of inertia. So there are two moment of inertias. This is actually the surface moment of inertia, that is the area moment of inertia. So this I is nothing but y square dA. So therefore you can write this integration of y square dA as I, and you can write this as m. Okay, it almost looks like Mary, M-E-R-Y. Okay, and then okay, so now so can you bring this to this format? So I wanted to derive m by I is equal to E by R. So just bring it onto the other side. So just bring it onto the other side. You get this as m by I is equal to E by R. So call this as equation how much? Here you call this as equation as 3. You call this as equation as 4. From 3 and 4. So from 3 and 4, you can write this bending equation. M by I is equal to sigma B by Y is equal to E by R. I think people may be confused. Where did the sigma B come? Guys, this sigma is the stress, and since the stress is due to bending, I call this as bending stress, and that bending stress is always normal to the surface. Normal means what? It is always perpendicular to the surface. So it is sigma n. All these are same. Sigma normal and sigma bending, all these are same. So therefore, you can write this final equation here, which is m by I is equal to sigma B by Y is equal to E by R, which is called as the flexure equation or bending equation, which is usually asked in most of the examinations. Okay, so by using this equation, you can solve for either bending stress in a material if you know moment of inertia and y, which is the maximum distance from the neutral fiber to the extreme fiber. Okay, so here this integration of y square dA, guys, last time you said that I is equal to BD cube by 12 for rectangular sections. If this is B, if this is depth is D, so I is BD cube by 12. So this is actually derived from integrating all the elemental areas dA, which is at a distance y from the neutral axis for a rectangle. If you actually derive this, you get this BD cube by 12. So this integration of y square dA is nothing but the moment of inertia, the surface moment of inertia. Basically I am saying, if I say I is more, that means area is more, and more than that, distance to that area is more because it is getting y squared. So if you want to have a beam which is very strong from the neutral axis, if it is the neutral axis, if you got more area, if you got this area here which has got more distance, so it is get y squared into dA. I will become more. If simply area becomes double, it is only going to double. If this y becomes double, I becomes 4 times. So when you are actually making a beam, nobody will make a beam like this because most of the area is very close to the neutral axis here. So area is there, but y is very small. So how will they make the beam? So beam will be like this. Beam will look like this. So have you seen a beam like this? So here the idea is that you got more and more area away from the neutral axis. More and more people. It is like, okay, imagine this as people contributing to GDP of nation. Okay, if more people earn more and more, then GDP will be more, no? So if I wants to be more, then these people should be very far away from the neutral axis. So that means they are earning lot. Okay, that means they are participating in taking load. So therefore, it is the reason why they don't choose a rectangular section. If you choose a rectangular section, all this material which is very close to the neutral axis, they don't take any bending stress, because you saw here neutral axis, they neither get expanded nor get compressed. It is simply staying as waste dead material. So it is not useful. So you want the fibers either at the top or either at the bottom, which will actually expand more or contract more. They will participate in taking loads. Okay. So therefore, for any beam to have more moment of inertia, more and more material has to be away from the neutral axis. Okay. So it is the reason in your scale also, if you hold a scale like this, you can easily bend the scale. If you hold a scale like this and suppose if you try to bend, so can you bend it? So give the scale. So here if I hold the scale like this, you can easily bend because all the material is very close to neutral axis only. If I hold the scale, neutral axis is at the center of the scale here, but this material is very far away from the neutral axis. Then they have to compress more and expand more. Here they have to compress more. Here they have to expand more. So they will participate. This material at the extremes will participate in taking loads. So they will take a lot of load. So in beams, so if this I has to be more, moment of inertia I is large when you keep it like this, but I becomes small when you keep it like this, because there is lot of area almost close to neutral axis which is waste. If there is a lot of area which is away from the neutral axis, then they will expand more or contract more, then they will participate in taking loads. So I will be more. So it is how this equation is related. So it is a very important derivation.